In this video, we're going to finally get to the last axiom of the real numbers, and that is the completeness axiom. We're going to look at the axioms that we have for real numbers so far. We're going to remember why we need another axiom in the first place. We're going to state the completeness axiom, and then we're going to use the completeness axiom to construct an irrational number. And by constructing a number, all I mean is proving that number exists using the axioms that we have. So the axioms for real numbers so far have sort of come in three parts. The first part was the arithmetic axioms, and when we put those all together, that made the real numbers a field. We then did the order axioms with the less than relation, and those made the real numbers an ordered field. And then finally, we demanded that the rational numbers be contained in the real numbers. And these are all great axioms. They're very necessary for the real numbers. However, they're also satisfied by the rational numbers themselves. And we need then another axiom to distinguish the real numbers from the rational numbers. How do we do this? Well, let's look at this set here, the set S consisting of all rational numbers, where when you square those numbers, you get a number less than 2. Now, if we use our intuition, it should be that the supremum of this set is the square root of 2. Despite the fact that square root of 2 is not in the set, it doesn't square to a number less than 2, and it's not even a rational number. But if that set does not have a supremum, that means the square root of 2 does not exist, and it's not consistent of how we think of the real numbers. So that suggests a possible new axiom that we can add to the real numbers, and that is every set of real numbers has a supremum. And that sounds great, except that if we look at, this isn't the only set for which this is an issue, but if we look at the integers, that's a subset of the real numbers. It does not have a supremum because it's unbounded, and so that axiom can't work. So we make some adjustments, we get a better axiom. Every bounded above set of real numbers has a supremum. And that one turns out to work pretty well. So I should first tell you what a bounded above set of real numbers is. If you have a set S that is a subset of the real numbers, we say that S is bounded above if it has at least one upper bound. You don't have to say about what the upper bound is. It doesn't have to be a supremum. It just has to be an upper bound. And then we say that S is bounded below if S has a lower bound. Again, it could have any lower bound, just at least one lower bound. So for example, if we want to be a little bit conservative and find an upper bound for the set S that we defined before, I'm going to claim that 2 is an upper bound for S, and that alone would prove that the set S is bounded above. So in order to do this, we assume that A is an element of S, and we show that A is less than 2. That would prove that 2 is an upper bound for S. So we know A is in the set. That means A squared is less than 2. And I'm going to make this a little bit easier for myself by noting that 2 is less than 4. And that implies that actually A squared is less than 4 as well. It turns out this makes things a little bit easier because 4 is a perfect square. If I subtract 4 from both sides, notice on the left side we have a difference of squares, which is easy to factor, and factoring is a great way of determining whether a number is positive or negative. So when I factor that, I get A plus 2 times A minus 2. That's just factoring a difference of squares. And since that is less than 0, and it's the two factors multiplied together, that means one of those numbers is positive and the other one is negative. And if you look at it carefully, it's pretty easy to determine which one is which. A plus 2 is the bigger of the two. That means A plus 2 has to be the positive one. A minus 2 has to be the negative one. And if we solve for A in both of those inequalities, we get A is bigger than negative 2 and A is less than 2. The one we were looking at is the A less than 2. We just showed that A is less than 2, and therefore 2 is an upper bound of S. Incidentally, if you look at that other inequality, so that means S is bounded above. If you look at the other inequality, we have that A is bigger than negative 2, which means that negative 2 is a lower bound. So that means our set S is not only bounded above, it's also bounded below. So now that we have our completeness axiom, here is our full set of axioms for the real numbers, and this is in detail just to make sure we have a full accounting for these axioms. So first of all, we have all the arithmetic axioms. Addition and multiplication are commutative and associative, and they both satisfy the satisfy the distributive property. We have additive and multiplicative identities, which we call 0 and 1. Every real number has an additive inverse. Every non-zero real number has a multiplicative inverse. And for the order axioms, we have trichotomy, which means if you have two real numbers, either the first one is less than the second one is less than the first one, or they're actually the same number. We have the transitive property, which means that if you have x is less than y and y is less than z, then x has to be less than z. We have translation variance. If you have x is less than y and you add the same number to z to both sides, you get x plus z is less than y plus z. And then you have the multiplicative version of that, scaling. If you have x is less than y and you multiply both sides by the positive number z, then xz is less than yz. We, of course, demand that the real numbers contain the rational numbers. And then finally, we include the completeness axiom that says if you have a non-empty set of real numbers that is bounded above, then that set of non-real numbers has a supremum. So we're going to use the real number axioms to construct square root of 2. In particular, we're going to lean heavily on the completeness axiom. So here's what we need. Right? We need to construct a set of real numbers whose supremum we believe is the square root of 2. We kind of already have one. You've seen one in the example before. We're going to have to prove the set is not empty, or else we can't apply the completeness axiom. We have to prove that the set is bounded above. And that will then imply, using the completeness axiom, that the set has a supremum. And then we prove the supremum of that set is actually the square root of 2. So, no surprise of what our set is. Now we're looking at the set of just all real numbers, such that when you square all the real numbers, you get a number less than 2. And we're going to show that the square root of 2 is the supremum of that set. But of course, the first thing in our we have to do is prove the set is not empty. It's pretty clear that 1 is in S. If I square 1, I get 1. 1 is less than 2, so 1 is in the set. That means the set is not empty. That's very important. S has an upper bound of 2. We proved that in the previous slide. That means that S is bounded above. We can now apply the completeness axiom. S has a supremum, and we'll call it beta. So now all we have to do is show that beta is equal to square root of 2. Now at this point, if I wanted to, I could give you a super clean proof about why this is true. But what I want to do with the rest of the video, it'll make it a little bit longer, a little bit messier, but I want to kind of show you the process that one might go through to prove that this is true. Okay, so we're going to go down some bad roads where we have to turn back and make adjustments, but I want to show you the process so you can see where these kind of unintuitive arguments come from. So we need to prove a couple of things. What is the square root of 2? Well, it is a positive number, so we have to prove that beta is positive. And when you square that number, you get 2. So proving it's positive actually is not going to be too hard. Remember, we have 1 squared equals 1, which is less than 2. That means 1 is in the set. We already proved that, but it doesn't hurt to prove it again. Since beta is an upper bound for the set S, that means beta has to be greater than or equal to 1. In particular, that means beta has to be greater than 0, so beta is positive. So that leaves us with the one task to do, which is to prove that beta squared is equal to 2. And this one's going to take a little bit of effort. So first of all, we're going to apply trichotomy. We want to show that beta squared is equal to 2, but beta squared could be one of 3 different things according to trichotomy. It can be less than 2, it can be greater than 2, or it can be the one that we want is equal to 2. And what we're going to do is we're going to prove it's equal to 2 by eliminating the 2 other possibilities. We're going to show that beta squared it can't be less than 2, and it can't be greater than 2. So let's try that. We'll start with the less than 2. So we'll assume that beta squared is less than 2, and then we'll try to find a contradiction. So if beta is less than 2, the question is beta going to be too small to be an upper bound of the set? That is probably where we want to go to find our contradiction. Right? Because we're assuming beta is an upper bound of the set, and if we make it so that beta squared is less than 2, hopefully we can show that beta is not actually an upper bound. So we want to find an element beta plus x, x being a positive number, so it's bigger than beta, where x is greater than 0, and we want to make beta plus x squared less than 2. So that's kind of a strategy that we might want to use. And so in order to show that, it can be helpful, as we've seen in previous problems that we worked on, look at beta plus x squared minus 2, and we want that, again, for positive values of x, and show that that can be negative. All right, so let's give it a try. So we know beta squared is less than 2, and if we subtract beta squared from both sides, that tells us that 2 minus beta squared is a positive number. Well, we were looking for a positive number x to add on to beta to see if when we square that, we get a number less than 2. Let's try x equals 2 minus beta squared. Where's the harm, right? So if I want to try beta plus x quantity squared and subtract 2, well, let's see. Our x is 2 minus beta squared. If we square that, oh my goodness, that is not very pleasant to look at. Let's try something else. What we might try, I still want to look at that 2 minus beta squared. It is a positive number. It has beta in it. It's something that can be really useful for me to use. I'm going to try to have 2 minus beta squared divided by a, where a is some positive number, and try to make that a big enough so that x is small enough to make beta plus x squared smaller than 2. And it might be helpful to have a be related to beta itself, right? So for instance, if we had a equal to beta, let's give it a try. If we did beta plus x, that is the same as beta plus 2 minus beta squared over x. If we find a common denominator and combine those, we get beta squared plus 2 minus beta squared over beta. And notice that those two beta squares cancel each other out, and we end up with 2 over beta. That's a really nice expression to have. So if I take beta plus x squared and subtract 2, beta plus x is 2 over beta. If I square that, I get 4 over beta squared. If we then combine those two, we get 4 minus 2 beta squared over beta squared. How about if we factor out a 2? That's kind of nice. If we factor out the 2, we get 2 minus beta squared, which we know is a positive number. 2 is a positive number. 2 minus beta squared is a positive number. Beta squared in the denominator is a positive number. Sadly, that makes it a positive number. We wanted it to be negative, right? So it didn't give us what we want, but a lot of things went right there. We had some really nice algebra workout. We were able to use the fact that 2 minus beta squared was a positive number to determine whether beta plus x squared minus 2 is positive or negative. It turned out to be positive, didn't work out. Oh well. What we really need to do then is to make our x a little smaller, which means we need to make that denominator a little bit bigger. So that's a bummer. It didn't work out, but let's try making that denominator a little bigger. So instead of 2 minus beta squared over beta, let's try 2 minus beta squared over beta plus 1. Right? Just make it a little bigger. See if that works. So if we do our beta plus x and do all our arithmetic and combining the fractions, turns out we get another pretty nice expression for beta plus x, beta plus 2 over beta plus 1. It's not too bad. So now if we take beta plus x squared and subtract 2, there's a lot of algebra. You can do the algebra. You can check it yourself if you want. You end up with 2 minus beta squared over beta plus 1 squared. Again, we get that 2 minus beta squared up there. We know that 1 is positive. Sadly, again, we get a positive number in the numerator and a positive number in the denominator, so that's greater than 0. So that didn't work out either. At this point, we may be getting a little bit dejected, but let's try one more time. Instead of beta plus 1, let's try beta plus 2, right? And it turns out that if we put beta plus 2 in the denominator, it will work. So here's what happens. We do beta plus x squared minus 2. If we do all the algebra, we get 2 beta squared minus 4 over beta plus 2 quantity squared. If we factor out that 2, notice now instead of having 2 minus beta squared in the numerator, we get beta squared minus 2. That's a negative number. So we get 2, a positive number, times beta squared minus 2, a negative number, divided by a positive number. That's a negative number, right? So we got beta plus x squared is less than 2. That means beta plus x is an S. It is bigger than beta, which means that beta cannot be an upper bound. That's our contradiction. So that means it's impossible for beta squared to be less than 2. If you do the beta squared greater than 2 case, that is going to work out almost identically. You're in fact going to do the exact same arithmetic. I'll leave that to you to do, but that one you can eliminate similarly. So you can't have beta squared less than 2. You can't have beta squared greater than 2. That means we have to have beta squared equal to 2, which means that beta is equal to the square root of 2. A lot of work just to show that square root of 2 exists. All right, so now I think you're ready to work on the activities for the completeness axiom. That's going to be at the link below this video.